Hello everyone, welcome to my video Converting Heat into Work about the Rankine cycle. I made a video about the Rankine cycle in German a longer time ago, and I decided to make an English version of this video. So I'm from Germany, so I hope you don't mind about my strange accent, and sometimes my English won't be that perfect. This video will be about the basic Rankine cycle, some basics you need to know about this to understand the whole process, how to work with the temperature, entropy and enthalpy charts. These are the T.s and h.s charts. I will show you how to calculate a Rankine cycle while using these charts for steam. I will show you how to calculate the efficiency of the Rankine cycle. I'll show you something about the reheating. You can skip the chapters by clicking here on these things here. I will show you something about preheating. We will not calculate anything in preheating because we'll have a separation of mass flow there, and it's too complicated to calculate this here in this video. And I will show you a full steam cycle, a real steam cycle used in steam power plants. So let's begin with some basics. In this video I will talk about water and steam, and green lines here in this video. A green line means a pipe filled with water, and the red line means this is a pipe filled with steam. And basically we have a condenser here, and this condenser, the exit of the condenser is water. And the first thing we do here, we take a look at, is this feed water pump here. And this feed water pump is pulling up the pressure here and pumping the water through this boiler here. In this boiler there's a evaporator which evaporates the water, and there's a superheater, and at the end of the boiler is superheated steam. So we just put in heat into our boiler, and at the end of the boiler we have superheated steam. Now there are some things here to talk about which are very important to understand. Isentropic, I will tell you about isentropic later in detail. And isobaric means isentropic, there's an insulation here and there's no heat exchange with the environment. This feed water pump is just adding the energy to pull up the pressure here, and an isobaric process means we have the same pressure everywhere. So this is just a pipe. It's not a real pipe, because if it would be real, this wouldn't be like that. We have the same pressure here along these pipes and in the boiler at every point. So if you have 200 bar here, you will have 200 bar here. This is the basic Rankine cycle. Something very important to understand. There's no pressure loss here, and there's no heat exchange here. So there was a viewer question at the last video I made in German, and I will explain this viewer question later. It's related to these facts here. You have an isobaric process and you just add heat here at the same pressure. This superheated steam will then be let in a turbine, and in the turbine you get out the work out of the steam, and you can drive a generator here. Out of the turbine there's still some steam, and the steam will be condensed to water in the condenser, and this way you will lose some heat energy here. You can't use this for anything useful. If you want to have a high efficiency for using work out of this, you can't use this energy here. You put it into a cooling tower or something. Sometimes they just put it direct into the river, but this is not good for the rivers. You shouldn't put up the temperature in a river. It's not good for the fish. Though that's what you see here. The energy that's coming out of the condenser is what you see in a cooling tower. And this condensation is happening at a constant pressure. You have no pressure loss here. You have the same pressure at the input of the condenser and at the output of the condenser. This is very important to know, that the pressure is the same here and it's the same here. So now let's talk about these words I used here, isobaric and isentropic. What do they mean? If we talk about thermodynamics, we often talk about ideal gases. The problem is, if I want to explain isobaric process, I have to talk about ideal gases to explain what's happening, and this might be a bit confusing now. This is a model of a gas. This gas is insulated at the right and the left here, and we have no insulation here. On top of this gas there's a piston or a mass m, and this piston is pulled down by gravity here on top of this gas. I can describe the state of this gas here with its volume, its pressure and its temperature. By the gravity and the force and the area here, the surface of this piston, I can determine the pressure that is on this gas, and so because of the gravity that is constant and the mass m that won't change, I have a constant pressure in this gas. So that's the basic thing for an isobaric process. I have a constant pressure. If I add some heat to this gas here, the piston will move up. The gas will expand while applying heat, and the piston will move up. So I will move the force, and I will move the force in the direction of the force, and this means I will put out work out of this. I can describe the new state of the gas now with a new temperature. It has a higher temperature, I put it in work there, and it has a bigger volume, yes, you can see here, but the pressure stays the same because I have the pressure is not determined by the heat, it's determined by the gravity and the mass m, and this will stay the same. I can calculate the new state of this gas with the volume, temperature and the pressure with these formulas here. You might already know them, they are very common in thermodynamics, these are the easy ones. And I get the work that I get out here with this formula, pressure multiplied with the change of the volume. This is not that complicated. If I use the force divided by the area for the pressure, I can insert it here for the pressure, and I see area. If I use the amount of the volume that is changed divided by area is the distance, and the distance multiplied with the force is the work that comes out. Everything I put into a system always is positive, and everything I put out of the system is negative. It's not always that, but it's a convention to have a uniform thing that is not too much confusing. So everything I put out, I pull out is negative, and everything I put in is positive. This is an isobaric process. Now the viewer question from the isobaric process was, if I put in heat and I get out work, I will get back to the Rankine cycle here. If I put in heat, where is my work here in this isobaric process? This is something that might be a bit confusing now. I put in heat here and I don't get work out of the isobaric process here. How is that possible? I will go back now to the changing the states of the ideal gases. The next process I will show you is the adiabatic process. It's pretty much the same like an isentropic process. It means we have a gas, and this gas is insulated and there's no heat exchange with the environment. We have a state of this gas, we can describe it with volume, temperature and pressure, and what we can do now is we can apply a force here, and if we pull down this piston here with our force, we will change states of the gases here, and with this insulation here we will change all three states. There's no heat exchange in this process, so this means the heat that is exchanged is zero, and the new states, every three variables have changed. We have a smaller volume, as you can see, we have a higher temperature, and we have a higher pressure. To calculate the new state, there are some formulas here. You already know them, or might not, but it's not important because here in the Rankine cycle we are talking about steam, and steam is not an ideal gas, so all these formulas here are not valid and we will not use them. We won't use any complicated formulas in this video, because this video is more about understanding the process, and there's not much to calculate with a lot of formulas here. So back to the viewer question, that was, how can there be work output in a Rankine cycle on an isobaric process? There's no work output on this cycle here. So the answer to this question, why is no work output here, is this is something. This is not a cycle like in an engine. This what you have seen here, changing states of ideal gases. This is in this animations I have a gas and I do something with it, and it stays at the same place. You can imagine like in an engine from a motor. You can't do it all at the same time, because you have to do it one by one. You have state 1, state 2, state 3, state 4. This is how an engine works, and this is what you do here. You have state 1 and you have state 2, and the gas stayed at the same position. In the Rankine cycle here, we have these processes happening all at the same. This isobaric heat addition is only possible not because the feedwater pump is pumping the water into here. It is also isobaric because the turbine is here, and if I would remove the turbine here, there would be no isobaric heat addition here, because there would be a lot of pressure loss here, because the steam would just come out of this pipe and the pressure would be dropping. So I have a constant pressure here because I have a turbine here that blocks the pressure from dropping here. This is the difference between the cycle you know from engines and the cycle in a power plant here. These things are happening all the same. This is not a cyclic cycle like in an engine. It's all happening at the same time, and the turbine here is the end of this isobaric process, and you get the work you put in here in the isobaric process. You get the work out of the turbine here. I hope this should be the answer to the viewer question, why don't I have work output here. I have the work output here at the turbine, and this is not a cyclic process like I said, like you have in an engine. So let's get back to the this process here. I want to show you how to calculate something about this, so I will show you the temperature entropy chart now. This is a chart that describes the states of steam, and we draw temperature over entropy here. This is important to know that you have lines here that have same pressures. This means if you have pressure of 1 bar, you will always stay on this line. If you have 10 bar, you will stay on this line here. All these lines come together here and go down here to this point. So if I get down the 150 bars, I go down here and they all go together here. This area here is the area of water. This area here is saturated steam. So we have a part water and a part of steam. If you go up here, this is a critical point. Below this point, above this point, you cannot say whether if it's a gas or if it's liquid. This area here is superheated steam, and this yes, it's everything. Superheated steam, superheated. This is supercritical steam. You call this area supercritical steam. This is the saturated steam, and this is water. X is the amount of steam in the steam. This x equals 0 means there's no steam, it's everything is water, and x equals 1 means everything is steam. And below this line you have superheated steam. These lines here show lines of constant amount of water or steam in the saturated steam. So another basic thing I want to show you is if you heat up water in a pot on your oven, you can just imagine, you can also do that. You can put water in a pot and put it on your oven and turn on the oven. Then you will heat up the water. If you put a thermometer into this thing, you will see that it takes some time and the water will reach 100 degrees Celsius. If you want to show this in this diagram, you have to know heating up water in a pot on your oven is on environment pressure. This means we have 1 bar. So we will go up this line here. We have environment temperature here, and we will heat it up to 100 degrees Celsius. This is here, and the amount of energy you need to heat up your water is the area here shown under this line here. And you can calculate the specific, everything here is specific, you see per kilogram here. You can calculate the amount of heat energy, specific heat energy you put in here by this formula here. So you just need to, you can use a triangle here and a square here. It's nothing complicated, so we won't solve any complex integrations or something here in this video. So if you heat up your water, you will see it takes some time to get to 130 degrees Celsius, and then if you leave your oven on, it will take a long time. It will really take a long time until all this water will be evaporated. It will take much more time than just heating it up, because if you follow this line here at 1 bar, while adding heat, you will go through these lines here, and this means your water will turn into steam. You will also cross these lines here. These lines show how much volume your steam needs, and it will increase the volume dramatically. You see here, you start here with about 0.01. If you have water, you have got 0.001 cubic meters per kilogram, and you see here, you will cross these lines too, and your water will take a higher volume. This is what you can see here if you cross these lines here. If I paint in the square here, this is the amount of energy you need to turn water from water into steam. And if you want to know how much it is, just take the square here. It's about 6.1 kilojoule per kilogram per Kelvin, and take the height here. This diagram goes down to 0 Kelvin, and you can calculate the square here. This should be about 6.1 multiplied with 373. You can remove this Kelvin here, and you get a number of 2275.3 kilojoule per kilogram. Don't write .3 here. This is not good to do this, because we just this is not very precise what we did here. If you look up the water steam heat, the specific heat, you see you need 2257 kilojoule per kilogram to turn water into steam, and that's what you can see here in this diagram. That's how to work, basically how to work with this diagram if you want to evaporate water. It's a simple task shown here in this diagram. You can also show the Carnot-process in this diagram. What is the Carnot-process? The Carnot-process is a theoretical process which is not using steam, so we will not use these lines we used with steam here, and it's describing a very fundamental thing about thermodynamics and about converting heat into work. If you want to convert work into heat, you can do this without any losses, because every loss you have in a machine is usually heat loss. And if you want to convert work to heat, there are multiple ways to do this. You always get 100% efficiency. This might be even if you use a generator and power electrical heating with the generator, you can get 100% efficiency, because you have the if you use the heat loss of the generator too, you have 100% efficiency. But it's not possible to turn this arrow around. It's not possible. So if you have a heat source and you want to take work out of the heat, you have to use a heat flow from the heat source to the heat sink to get work. And the Carnot-process is describing how much work can I get out of a heat source by using a heat flow from a heat source to a heat sink. If I have the temperature difference of this thing. The Carnot-process in this is a theoretical process. It doesn't exist, but I will try to explain it to you. The first thing you do is you put work into a gas without exchanging heat energy. You just put in work and compress the gas. The next thing is you put in heat, and you put in heat at a constant temperature. This works by expanding. You let the gas expand. You put in heat and the gas will expand. This is an isothermal process. This is possible. And if you want to know how much heat energy you put in here, just calculate the square under this line and you get the specific heat you put into this isothermal process here. Next thing is you let your gas expand again, but this time you pull out the work out of this process and you do this insulated again, and there's no heat exchange. At the end you need to compress it, and by compressing the gas it will there will be a heat output out of this, and this will be happening at a constant temperature. It's the same like here, but the other way around, and you get heat energy out of this. And the difference between this is what you see here on the square is the work you can use from these four steps here. There's a formula to describe the maximum efficiency you can get with a high and a low temperature, and this formula is fundamental of thermodynamics. It's very important. It describes the maximum efficiency with two temperatures. Now I will show you the Rankine cycle in this temperature entropy chart. So we will, if we use steam, we can't draw the Carnot-process here, because our lines of constant pressures, everything is defined here because we use water and we use steam. If we want to paint this thing here into this chart and use it for a calculation, I will start to add some values here. The first thing that we do is compress the water. So I start this process with water of 50 degrees Celsius, and at 50 degrees Celsius the steam pressure is 0.124 bar. This means this pressure means I can always have a higher pressure here, but if I would lower the pressure, the water would evaporate. The same as if I would try to add some heat here, I would evaporate the water too, because at 50 degrees Celsius and 0.124 bar, this water exits the condenser, and the condenser just condenses the water. It doesn't cool it down. So this is water that if you add some heat here, you will get steam again. This water will be pumped into our boiler here, and by doing this, I just thought about 25 bar. This is what I put in this value, and with 25 bar I get 50.086 degrees Celsius. So if I want to draw a line here, you see 300-400 Kelvin, and this is 0.086 Kelvin, a difference here from the temperature. You cannot paint it into here, so that's why I will not paint it here. There are many books where you see a straight line up here, but in reality there is no line from a feed water pump here in this diagram. It's not possible to paint this here. So how do you get these values? I just will show you later how to get these things. I just explain this to the end here. The next thing is I said I will heat it up to 520 degrees Celsius, and the pressure stays the same. If I do this, I can draw this here. I will add heat, and heat addition means the entropy is rising because I'm adding heat. So I go up this line here of constant pressure at 25 bar. I heat up my water, I evaporate my water, and I superheat my steam. That's what you see here. This superheated steam will get to the turbine here, and in the turbine, if it's the simple process like that, there's no heat exchange in the turbine. This means the entropy stays at a constant value. Just pull a line down here, and I go down to 50 degrees. This is my starting point. I have the same pressure like at the end of my condenser, because the condenser goes right here at the end of the turbine and condenses the water at a constant pressure. And this pressure here is the same pressure like here. You see, these are the same values here. I have an x of 0.91. This means 91% steam, and here I have 0% steam. And I just this conversation from 0.91 to 0 is what the condenser does. I can calculate the efficiency here by painting some squares and some triangles. It's quite easy to paint them here. And if you calculate this area here, the squares and triangles, you get this number. This is the heat you put in, the specific heat you put in, and this square here is the specific heat you put out. You can calculate the efficiency of this process now like this. You just look how much heat you get out by taking that what you get in minus what you get out, but you have to make an addition here because you have minus here, and divide it through the whole energy you put in, and you get an efficiency, you can add these numbers here, of 0.346. This means 34.6%. This is the efficiency of this. Now we could just try to use higher values. Just use 150 bar and something. I will show you this like this: 150 bar and 520, and I would get efficiency of 45 or 43% out of this diagram. But this is not possible, because if you look here, this would be possible, that's no problem, but this here means your turbine is using superheated steam. That's how what turbines are built for. And here you will get your turbine is not able to handle saturated steam with 75% water, 75% steam. This means 25% water, and 25% water like this here will destroy your turbine. This is not possible to do the process like this. That's why you won't find a diagram like this in a real power plant. Sometimes you find a diagram like this in some books for explanation, but I want to use a diagram like this because these are some values you can use in a real turbine, even it's not that efficient. If you would do like this, you would have a high efficiency and there's no need to do something else, but we want to have a higher efficiency later in this video. I will talk about the exit of the turbine later when we talk about reheating. But next we will just paint these things into the enthalpy entropy chart. This chart looks a bit more confusing than the chart we used before. We have an area of water here. We have an area here with the saturated steam. We have these lines who show us how much steam is there in this saturated steam. We have the superheated steam here. We have lines of constant temperature now, and we have lines of constant pressure. This looks more complicated now. We can zoom in this area here. This is how you may find these diagrams here, or these charts. You have lines of constant pressures and lines of constant temperatures. So you have to find the point from your process here in this diagram, and you can look up the enthalpy here. These are the German words for enthalpy and entropy, by the way. I didn't want to make the these charts new just for the new video. That's why I'm using degrees Celsius and bar instead of degrees Fahrenheit. It's too complicated for me. But anyway, this chart is easier to use, and I will show you why. If we put this process here in this chart, it will be the same here again. I cannot see the feed water pump in this chart because it's too less to show in this chart. It's just a little bit of enthalpy I get here by the feed water pump. But I can paint in the isobaric heat addition I have here in my evaporator and my superheater. I just go up the line with the constant pressure here at 25 bar. I go down in the turbine on a constant entropy here. I have a straight line down here, and this is the line on the constant pressure from the condenser. Now this diagram is pretty easier because you can calculate the efficiency in this diagram. You just need to calculate the values here from the enthalpy here. If you zoom in this area here, you can see this. This is our feed water pump in the h.s-chart. You see, it's not that much of an enthalpy difference you see here. If you look up all these points, you have you have the steam properties here, 50 degrees and 0.124 bar, and you can put them into this diagram here and look up these steam properties here, and you get out by knowing pressure. If you know the pressure, the amount of steam, or if it's superheated steam, you know it's superheated steam, everything is fine. If you know it's saturated steam, you have to know the amount of steam you have, and by knowing this amount or the state of the steam, or if it's water, the temperature and pressure, you can calculate the enthalpy. You can just read, look it up in this chart, or I will show you how to get an exact value in a few minutes. If you look at the feed water pump, you can look up these two states, and you see you have 3 kilojoules per kilogram in your feed water pump. At the end of the boiler, you have 3,507. I will show you now how to get 3,507. Just go back, and you see you have 25 bar and 520 degrees Celsius. So if I want to know exactly how much I have, I use a tool for MATLAB. You can get this tool, by the way, you can see how I'm recording this. I'm using Linux, but I still have this presentation as a PowerPoint presentation, so I have to emulate Windows 7. Just search for xsteam on Google, and you will find an M file at MathWorks. And with this M file, I also created all these charts you see in this presentation. Download the zip file here. You can open it, and you need the xsteam.m file. So just extract it here on my desktop. There it is. And if I open it, you can see there's some in the comments is how to use this xsteam function to get exact values. This is what the steam table can calculate you. We want to calculate the enthalpy by pressure and temperature. This is this one here. I don't have MATLAB for Linux here, but I use Octave. This xsteam file is compatible to Octave. So just open a terminal, open Octave. Windows users may load it in MATLAB, and we can calculate the specific enthalpy by typing in xsteam. Then we're telling them what to do. We want to know the enthalpy as a function of pressure and temperature. We tell them a pressure of 25 bar and 520 degrees. Just return, and we get 3,507. This is how you can get exact values for this. There are also some mobile apps for your smartphone where you can get the enthalpy of pressure and temperature. But it's not necessary to do it that precise. It's okay if you just read here in the charts how to get to these how much these values are. In reality, you have pressure loss and you have heat losses, and your results don't need to be that precise. So you can calculate the amount of energy, specific amount of energy you get down in your evaporator, in your steam superheater. Let's get down here to the turbine, and you see here the end of the turbine has a specific enthalpy, and if you can just calculate it by subtracting these values, it's pretty easy. And if you want to calculate the efficiency, just put in these values, the amount of work you get out of the turbine, subtract the amount of work the enthalpy you put in the feed water pump, just subtract these values and divide it by the amount of heat you put into this, and you get your efficiency here. This is the easy way to calculate the efficiency, even if the h.s-chart looks a bit more complicated. So now let's go back to some basic things. I told you in the beginning that I can show you this again. It was the simple Rankine cycle here in the T.s-chart. I just want to tell you that this is not, I just told you that this is not possible, and I use this one here, and now I will show you how to get a more efficient process without doing the process like this. What I'm doing now is I'm reheating the steam. Calculating Rankine cycle with reheating. There we go. So it's pretty much the same, but after the boiler and the turbine, we call this a high pressure turbine now, the steam will not exit the turbine as saturated steam. It will still be superheated steam, and the superheated steam will be put back into our boiler in our superheater and will be heated up again. That way I get out superheated steam at a low pressure. And if we look at the okay, you know what's happening now. You have isentropic and isobaric processes everywhere here. That way you can paint the process like this. You have the feed water pump, you have the isobaric heat addition here, and now we do not pull. You might remember the last picture, the line was going down here and this was not possible. I will end this line here and pull the steam back into a reheater. In this reheater, the superheated steam will be heated up again like this to a high temperature here, and then it will go to a second turbine, and in the second turbine it can expand until it can enter in the condenser for the condensation. And that way I won't have a high amount of water in my steam here. That's why you do reheating. You don't do reheating for getting a better efficiency. You do reheating because you need to do it if you want to get a high efficiency by using higher steam parameters like this one. It's not possible to go down here because it would destroy your turbine. This is why you use reheating. And you see it's pretty much the same. You have isobaric and isentropic process here, and you see the input of the condenser is the same like the output. Temperature and pressure, only this thing changed from x to 0.91 to 0 because we have saturated steam here and water here. It's pretty much the same. If you want to calculate the efficiency, it's the same too. Just put in squares and triangles here and calculate the amount of area you see here. You can calculate the amount of area here. So this is what you put in, this is what you put out. You know this formula from the previous chapter, and you get an efficiency of 43.5%. This is pretty much. If you want to do it more precise, you can also paint this Rankine cycle in the h.s-chart like this. I just click it through here. You know how this works now, and you see this. It's pretty easy now to calculate the efficiency in the h.s-chart because I just have to look all these values here. I showed you how to use a MATLAB script. You can also use these charts here. KSP is a German word, Kesselspeisepumpe, for the feed water pump. I just forget to change this here, and you see this is the amount of specific enthalpy from your evaporator, from your turbine here, and this is the high pressure turbine. There comes the reheating process, and there comes the low pressure turbine here. So you have the amount of specific enthalpy in your low pressure turbine. You put in this in a formula. This is what you get out from your turbine minus what you put in your feed water pump, divided through the whole energy you put in to this process, and you get the same value by this. But this is more easy. Even if it looks complicated, it's more easy to do this because you just need to search for these points here. Everything, if you have to calculate something like this, there will be enough data for you to draw these lines like this here. You just have to look up where your steam properties are and read the enthalpy here from this axis here, and you can calculate the efficiency. To get a more efficient Rankine cycle, you can you remember you just everything you have the end of this turbine, and everything of the energy here in this condenser is lost. Now you can use a turbine tap. That's called a turbine tap here. You can use a turbine tap and use steam from the turbine here to preheat your water. That way not everything that at the end of the turbine is condensed, and the energy you use here is not lost, because everything you pull out of the condenser here will be wasted into the environment. And the first thing is you need two pumps now, because if you would heat up the water at the end of the condenser, it would evaporate again. So the first thing is you need a condensation pump here, and this condensation pump will pump the water through this preheater here, which gets its steam out of the turbine here. That way you can raise up the efficiency. For if you want to paint this in the T.s-charts, you have this is now I'm not using values anymore, because now it would be too complicated to calculate this, because the mass flow is no more constant, because you split up the mass flow here in this area. This is the compression, compression is isentropic compression of the condenser pump here, and you can now preheat your water here. This energy here you see here has not to be used. Has not be burn. You don't need to burn coal or split atoms or something to heat the water up here. You use it from your turbine here. If you just paint the rest of the process here, you can see you just take the steam here, and you will paint the rest here. So that's your process now. You have first the condensation pump, your preheater, the feed water pump, and your evaporator with superheater. And you take at the end of the turbine, you can't use a lot of energy is wasted, because you can't use all of this. This is too much water here. You just take out the steam here and use this energy here that is condensed, this energy from the condensation, and use this to warm the water here. That's how preheating works. The full Rankine cycle, or it's no more Rankine cycle, the full process in a power plant looks like this. So you have a big, let's start here, you have a big tank here where you store your water, because you have to fire up your power plant sometimes. It's not running all the time. You store your water here, and this water will be pumped with a feed water pump. The feed water pump can be driven by a turbine itself. You take the turbine from a tap at your turbine here. There's the steam taken out from the turbine, and you have high pressure preheaters here, which also take steam out of the turbine here from this turbine tap. And you see there's no more constant mass flow rate. The boiler consists of multiple. You have a boiler itself, and you have superheaters. You can control the superheaters by using water here and injecting water into before the superheaters. That way you can control the output temperature of your boiler. And this same is for the reheater. You just put in water here to control the output temperature of your reheater. Using this water here is bad for the efficiency, so it's important to not to use a lot of water here. So you have to design your power plant to get a high temperature here without using water here. It's very difficult. And you see you have another preheater here. This is a low pressure preheater because it's on the low pressure side. This is the high pressure preheater because they are on the high pressure side. Just added some values here. These are not real values. These are so you can just some values that you can imagine how much pressure and which temperatures we are talking about. It's still some ideal values. If you paint this into a diagram, it looks more like this. You have the you don't have a constant mass flow rate. This is why it's not possible to calculate it by using these triangles here. And you can see here these areas here at the beginning. This is what your preheating does. It's just this area here is from the preheating. You don't need to use coal or nuclear fission to to heat the water up in this area here, just from here up to here. And this is how to raise the efficiency a bit. So that's quite everything in this video. Oh no, it's not quite everything. This is some detailed view of this thing. This is how it looks in reality. That's the end. Okay, I hope you enjoyed this video. I hope you learned something, you liked it. Leave some comments in the comments area. This is my first video in English now. I hope you have understood everything. I hope it didn't make that much mistakes. Thank you for listening, and goodbye.